approach for quantum Fisher information, please.
Thank you for the introduction. Today I'm going to tell you about our recent work on the resource theory of asymmetry in the non-ideal regime. And the resource theory of asymmetry is a branch investigating energy coherence, and the target of the study is a general asymptotic theory for the limitations on the distillation and dilution of energy coherence. And to obtain this result, we constructed an extension of information spectrum method that is valid for quantum Fisher information, which is a standard measure of energy coherence. So this work is done in collaboration with Tajima at the University of Electrical Communications, and the technical detail can be found in this preprint on arXiv. Okay, so let's get started. First, what is energy coherence? Well, it is a superposition between energy eigenstate of the Hamiltonian with different energy eigenvalues. For example, this resource is mandatory for creating accurate clocks, accelerating quantum operation, and measuring quantities that do not commute with the Hamiltonian. And applications to these topics are out of scope of this talk, so I will not go into detail here. A branch of resource theory analyzing the nature of energy coherence is called the resource theory of asymmetry. And I will provide a concrete definition later, but this resource theory is used to investigate the sequence of the symmetry of dynamics and the conservation models. And in any resource theory, one of the fundamental issues is to determine the limitation in manipulating the resource. And there are two important operations, distillation and dilution. And as you may know, the distillation is an operation of extracting as much resource as possible from a given state. And for example, this is important in repairing damaged resource. And dilution is the opposite operation. That is the operation of creating a desired state by consuming as little resource as possible. And in the resource theory of asymmetry, several important results on the resource manipulation are known. For example, the exact convertibility conditions among pure states are derived in terms of energy distributions in these papers. And in a recent study, the asymptotic conversion theory for i.i.d. states are established here. And although this result in the i.i.d. regime is important, it cannot be applied to a realistic situation where resources typically have complex correlations. And therefore, the conversion theory that is valid beyond the i.i.d. regime is essential. And however, resource conversion theory in the non-ideal regime in the resource theory of asymmetry has not been established so far. But in some of other resource theories, such as entanglement theory, non-ideal theory has already been established. And this is done with the so-called information spectrum method. The information spectrum method is a powerful method to analyze the non-ideal regime for problems related to entropies. For example, in entanglement theory, in the non-ideal regime, the entanglement cost and the disturbed entanglement shown to be equal to the so-called spectral Superman and inframan entropy rates, which is denoted by overlying S and underlying S. And I'd like to emphasize that this result holds for any sequence of pure states. Although the information spectrum method is so powerful, it has not been possible to apply it to the resource theory of asymmetry. This is because that a standard measure of energy coherence in the resource theory of asymmetry is quantum Fisher information, which is quite different from the entropy. So to establish the non-ideal theory in the resource theory of asymmetry, we have proposed an information spectrum approach that is applicable to the quantum Fisher information. So there are three main achievements of our study. First, we introduced new quantities, which we call the spectral Superman and inframan quantum Fisher information rates. And they are the counterpart in the resource theory of asymmetry to the spectral soup and in entropy rates. And second, to construct these quantities through the smoothing method, we define the maximum and minimum quantum Fisher information. These two have similar properties to the maximum and minimum entropies. And third, to show the properties of these quantities, we introduced the notion of asymmetric modularization for probability distributions. And we showed that the exact compatibility among pure states in the resource theory asymmetry is expressed by using an asymmetric modularization relation. And so this is a counterpart in the result theory of asymmetry to the Newton theorem in entanglement theory. Okay, so here's the outline of my talk. I have completed the introductory part and a short summary of our achievement. And I will now provide a complete definition of the result theory of asymmetry. And then I will introduce the spectral quantum Fisher information weights. And by using them, I state the main theorem, which relates the coherence cost and disturbed coherence to the spectral quantum Fisher information weights. And finally, I will provide an intuitive explanation of this result. Okay, so let us begin by identifying state with and without energetic coherence. Consider a system with a Hamiltonian edge. And as I have mentioned, the energetic coherence is a superposition of energy eigenstates with different energies. And therefore, a state has energetic coherence if and only if it evolves by time evolution generated by the Hamiltonian. We call such a state asymmetric state. On the other hand, a state without energetic coherence is invariant under time evolution. So this is, of course, equivalent to say that the state is diagonalized in an energy eigenbasis. And such a state is called symmetric state. So to manipulate energy coherence, let us now consider the transformation of state. And a basic element is an operation that does not create energy coherence in the sense that it transforms a symmetric state to a symmetric state. So this condition is satisfied if a CPTP map E satisfies this condition. And this can be checked as follows. For symmetric state, low, since low is invariant under time evolution, this equation holds. And by using this condition, this also implies that E low is invariant under time evolution. So if the state low is symmetric, then E low is symmetric. And we call such we call such a CPTP map covariant. And based on these ideas, let us now define the result theory of asymmetry. And of course, as you may know, any result theory is defined by its free states that can be freely performed and the free operations that can be freely added. The free states that can be freely prepared and free operations that can be freely performed. And in the result theory of asymmetry, free state is symmetric state and free operation is a covariant operation. And any state that is not free is regarded as a result state. So the result state in the result theory of asymmetry is asymmetric states. And this construction is, of course, the same as the entanglement theory, where entanglement becomes a result by defining separate state and LCC as free. Okay. And in any result theory, it is essential to find a good measure to quantify the results. And in general, quantity R is regarded as a resource measure, is called as a resource measure when it satisfies two conditions. First, it monotonically decreases under the free operation. And second, it vanishes for any free state. In the resource theory of asymmetry, a standard measure is the symmetric logarithm derivative quantum Fisher information with respect to the state, a family of states generated by the time translation. And conventionally, by using the eigenvalue composition, it can be the explicit form of this quantity is given by this equation. And conventionally, this quantity is simply called the quantum Fisher information. And for pure state, the quantum Fisher information is proportional to is given by the 4 times the variance of energy. And in general, so this is a quantifier of the quantum fluctuation with respect to energy eigenvalues. So here, as a side note, let me briefly mention about the difference between the result theory of asymmetry and the result theory of coherence. Let us now consider a harmonic oscillator system with this Hamiltonian, and let us compare these two states. The psi1 is given by the superposition of the ground state and the first state, and the second one is given by the superposition of ground state and the second excited state. And in the result theory of asymmetry with this Hamiltonian, these two states are not interconvertible. This is because that these two states has different quantum Fisher information. And as I have mentioned, the quantum Fisher information is a resource measure in the result theory of asymmetry. So if these two has different quantum Fisher information, then they cannot be, they are not intercompatible. On the other hand, in the Risto theory of coherence, not let us consider the Risto theory of coherence with respect to the energy eigenvalues. And of course, there are several different formations for the coherence theory, but here let us use the so-called maximally incoherent operation as a free operation. So this is a set of all channels that maps diagonal state to diagonal state with respect to some specific basis. And with this definition, it can be easy to see that all covariant operation is okay. It's a maximally incoherent operation, while the opposite is not true. And in the lesser theory of coherence, these two states, and the psi1 and psi2 are interconvertible, since the operation of exchanging the first excited state and the second excited state is maximally incoherent operation. So to summarize, a crucial difference is that in the Risto theory of asymmetry, we care about the energy eigenvalues in addition to the energy eigenbasis. But in the Risto theory of coherence with respect to this basis, we only care about the basis. So this makes the analysis of the Risto theory of asymmetry complicated. Okay. So now let me clarify the setup of conversion theory in analysis. And hereafter, for simplicity, we assume that the Hamiltonian of the system is given by the harmonic oscillator Hamiltonian. And it can be shown that the convergence theory for harmonic oscillator system in a pure state can be generalized to any system in periodic pure state with an arbitrary Hamiltonian. So here I provide an intuitive explanation how this works. Suppose that we have a pure state which has a finite period tau with respect to a Hamiltonian x. And let us first rescale the Hamiltonian by multiplying tau over 2 pi so that the state has a period 2 pi. And in this figure, the solid and dashed line represents the energy level of this rescaled Hamiltonian. In particular, the solid lines shows energy level that are included in the support of the state psi. And by using the fact that the state psi has a period 2 pi, it can be shown that the energy gaps for these solid lines are integers. And to obtain the harmonic oscillator Hamiltonian, we first eliminate the energy levels outside the support. And in addition, we add energy level so that all energy gaps become 1. After this operation, we obtain the harmonic oscillator Hamiltonian. And it can be shown that such an elimination and addition of energy level does not affect the convertibility if we only change the energy level that lie outside the support of state. So in this sense, harmonic oscillator Hamiltonian is a standard Hamiltonian to analyze the convertibility among pure states with finite periods. So hereafter, I will always assume that the Hamiltonian is given by this equation. Okay. So now we will analyze the asymptotic convertibility with vanishing error in the asymptotic region. And we adopt the trace distance as a quantifier of error. And we say that a sequence rho is convertible to another sequence sigma by covariant operation, if and only if there exists a sequence of covariant operation that maps state rho to a sigma with vanishing error in the asymptotic region. And in this case, we denote rho hat succeeds sigma hat. And we introduce two key quantities, the coherence cost and the disturbed coherence. And they are the optimal conversion rates from and to reference state, which is defined by these equations. And here we adopted coherence B as a reference, which is given by the superposition of the ground state and the first excited state. And phi hat R is a sequence of coherence bits where a positive number R describes the rate at which the number of coherent bits increases. And in the i.i.d. regime, as I have mentioned, these two quantities have been calculated, and it is known that the coherence cost and the disturbed coherence for pure state is given by the quantum Fisher information. However, in general, these quantities does not necessarily coincide with each other, and a general formula for these two quantities in the non-i.i.d. regime is the main target of our analysis. So here, for later convenience, we introduce several notations. First, for given pure state psi, its energy distribution is denoted by peak psi. And in the convergence theory, energy distribution plays a key role since any pure state is reversibly convertible to this state, which implies that the convertibility can be fully characterized by this energy distribution. So I should have write peak psi here. Sorry about that. And for sequence of numbers, we define the convolution product by this equation. And for given sequence Q, we say that another sequence Q tilde is an inverse sequence if it satisfies this equation, where delta denotes the Kronecker delta. And so this is the inverse with respect to the convolution operation. An important thing is that such an inverse sequence can be constructed explicitly by using a recursive formula, which I am not showing here, but if the support of the sequence is bounded below. And as we shall see later in analysis, the inverse sequence for energy distribution plays an important role. Okay. So the last key element to construct the information spectrum method for the quantum fission information is the generalized Poisson distribution. For real number lambda, we define p lambda by this equation. When lambda is non-negative, it is an ordinary Poisson distribution. On the other hand, when lambda is negative, this is not a probability distribution since it becomes negative when n is an odd number. Nevertheless, it turns out that this quantity is of fundamental importance since p lambda tilde is given by p minus lambda. Okay. So now we are ready to construct the information spectrum method. We introduce the maximum and minimum quantum fission information for pure state by this equation. And intuitively, these two quantities gives the amount of energetic coherence in psi that can be transformed from and to a pure state whose energy distribution is given by the Poisson distribution. And I will come back to this point later. And also the maximum we extend the definition of the maximum quantum fission information for a general state by using other infimum over the purification of the state. And also, this point is also explained in later. And these two quantities, I mean the maximum and minimum quantum fission informations, have similar properties to the maximum and minimum entropies. For example, they give an upper bound and lower bound for the quantum fission information for any pure state. And by using these two quantities, we now define the spectral, supermum, and infimum quantum fission information rates by these equations. Here, Fmax epsilon and Fmin epsilon are defined by using epsilon balls. And for maximum quantum fission information, we use the ordinary epsilon ball. But for minimum quantum fission information, we use the epsilon ball for pure states since we have defined minimum quantum fission information only for pure states. And it should be noted that our definition for the spectral quantum fission information rates are very similar to the spectral entropy rates expressed with the smoothing method. In the smoothing method, we introduce a smoothing parameter epsilon, which roughly speaking quantifies the error. And from the minimum and maximum entropies, we can define the smooth maximum and smooth minimum entropies by the equation. And the spectral entropy rates are defined as the asymptotic rates with punishing error. So this is the reason why we call these overlying F and underlying F as spectral quantum fission information rates. So by using these two quantities, the main result of our paper is stated as follows. For any sequence of pure state, the distributive coherence, the coherence cost is given by the spectral supermum quantum fission information, while the distributive coherence is given by the spectral infimum quantum fission information rate. And in fact, this result shed light the correspondence between the resource theory asymmetry and the entanglement theory. in the list theory of asymmetry, the central quantities are the quantum efficient information and its variant. But in the entanglement theory, various entropy plays essential roles. Although the quantum efficient information and entropy are quite different, our result shows that the conversion theory in the non-ideal regime has a similar structure, both in the Aristotle theory of asymmetry and the entanglement theory. Okay, so now to provide a rough sketch of the proof of a main result, I will further explain the detail of analysis. And a key notion is asymmetric majorization. For a given probability, for given two probability distributions P and Q on integers, we say that P asymmetrically majorizes Q if and only if the convolution of P and Q tilde is positive. And in this case, we denote P succeeds Q. And it is shown that the such a majorization relation is a pre-order. A key property of this majorization relation is that the necessary and sufficient condition on the convertibility between pure state by covariant operation is given by an A majorization relation of energy distributions. So this is a counterpart of the Nielsen theorem in entanglement theory, which states that the exact convertibility by LOCC is given by the majorization relation of the Schmidt coefficient. So by using the A majorization, I will now explain the interpretation of the maximum and minimum quantum efficient information. We define the maximum quantum efficient information by this equation. The condition we import here is the A majorization relation. So we can rewrite this quantity in this way, where chi lambda is a pure state whose energy distribution is given by the Poisson distribution. Since the variance of the Poisson distribution is lambda and the quantum efficient information of pure state is 4 times the variance, we get the expression in the last line. So this means that the maximum quantum efficient information is the minimum amount of energetic coherence quantified by the quantum efficient information in chi lambda that is required to create a pure state psi. And similarly, the minimum quantum efficient information is given by this equation. So this means that the minimum quantum efficient information is the maximum amount of energy coherence that is required, that can be extracted from a pure state psi. So this, based on this, essentially, so based on these observations, we can show that the spectral and inhuman spectral supremum and inhuman quantum efficient information rates capture the coherence cost and the disturbed coherence. And of course, the detailed proof is more complicated, but I will not present it here. So for technical details, please check this paper. And before concluding my talk, I will finally comment on the cost of creating mixed state. So to be specific, let us analyze a minimal cost that is required to mixed state law from a pure state chi lambda. Since the partial trace is a covariant operation, it is easy to see that the cost required to creating a purification philo is greater than the cost of creating the state law. And furthermore, by using the covariant Stein-Spring dilation theorem, we can show that the infimum of the cost of creating the purification of law is less than or equal to the cost of the state law. And I think I will skip the detail here, but what is important is that based on this result, we see that the cost of creating law is equal to the minimum cost of creating the purification of that state. So this is the reason why we define the maximum quantum efficient information for a mixed state by using the purification. And essentially based on from the same reason, it can be shown that our result for the coherent cost for pure state can be extended to a mixed state. So that is the coherence cost for any sequence of state is given by the spectral Superman quantum Fisher information rate. This is defined by this equation. Okay, so here's a summary of my talk. We have established conversion theory in the non-ideal regime in the resource theory of asymmetry for pure state by using the spectral soup and in quantum Fisher information rates. And as I have mentioned, the result for closed can be directly extended to a general sequence of state. And to construct these two quantities through the smoothing method, we define the maximum and minimum quantum Fisher information. And we introduce the asymmetric majorization relation. And by using this notion, we have shown we have provided an interpretation of the maximum and the minimum quantum Fisher information. And the important thing about the asymmetric majorization is that it gives a necessary and sufficient condition for the exact convertibility among pure state, which is a counterpart to which correspond to the Nielsen theorem. Okay, that's it. Thank you for your attention.
Okay, thank you very much. Questions?
Yeah, I have a question about your definition in the case of mixed state. So in the paper, the way I define it is in terms of the cost for preparing state rho is in terms of the rate of consumption of pure states in the same frequency.
Yes.
And I explained that why purification. If you think about the purification, it won't be the optimal strategy. Basically, to minimize the variance, if you want to minimize the variance, you obtain the purification, which will not be periodic in general. So I guess I'm confused about why you define Fmax, or why do you define cost in terms of purification? Like why you don't take the the standard definition in terms of the rate of interconversion from pure states to the mixed state rho?
Do you mean that maybe I think I should explain this part in more detail? Is that?
Yeah, maybe. Yeah, I mean, just this definition. I mean, why usually in resource theory the way we define the cost, is in terms of the rate of interconversion from pure state to your fixed pure state to the desired state rho. So, but you're changing that definition, right? Is that you're not
well,
standard definition?
You mean that maybe I think your suggestion is that instead of this definition, we may use just this one as a definition, even for mixed state. Is that your point?
I mean, I'm just suggesting, usually we define it operationally in terms of the minimum rate of resource that you need to consume to prepare the copies of those states. Okay. And I studied that, in the i.i.d. regime, I studied that for, and I calculate, and I showed that this would be quantum Fisher information of that mixed state rho.
Yes.
But it looks at here, you are using a different definition for mixed state rho. You're just saying, let's look at the purification of rho as the cost. Is my understanding correct or?
Well, so I think your concern is the definition for the maximum quantum Fisher information for mixed state, right?
That's right.
Yeah. So we just wanted to make it consistent with the pure state, and we thought that an important thing about the I mean, I think your suggestion is Your suggestion is just we can simply extend the Fermat's law by using this situation, right?
Well, I'm suggesting why we don't just think about the standard operational definition in terms of the rate of consumption of pure resource states. Why we change the I'm just asking. I couldn't understand, I guess, from your talk.
Well, I think so. I think I understand, but our motivation is to yeah. I think so that kind of definition is also fine, but if you define in an operational way, in the sense of that the minimum consumption of the resource to construct a state by a covariant operation, then so the definition includes something about the existence about the covariant operation or something like that, right? And
Correct.
In that case, it is quite difficult to compute such quantities because we have to explicitly construct the covariant operation for each state or something. So that's something we wanted to avoid. So we wanted to make everything in terms of protocol, which can be calculated, at least in principle.
I agree that it will be difficult in general. I did the calculation for i.i.d, but I agree that it will be difficult in general. But that's the standard way of defining the notion of resource cost. It will be a difficult calculation, but I suggest maybe we don't change the standard definition just because it could be complicated for the audience.
I think the left-hand side of a main result is an operational definition. So these quantities are operationally defined by using the conversion, right? And we want to make it to a more quantities that can be calculated at least in principle, rather than mentioning about the existence of covariant operation or something like that.
But the issue with this definition is that it doesn't give the i.i.d result that in the i.i.d result I showed that you get quantum Fisher information of rho, but if you look at the purification, then you get a larger number than quantum Fisher information of rho. It will be in general larger. If I understand correctly, you are preparing the purified version of the state. Is that right?
Yes.
Okay. And in general, if you use that strategy, I discussed this briefly in the paper, but if you use that strategy, the cost will be higher than quantum Fisher information.
So do you mean that this result is invalid?
I'm not sure if I understand this result, but what I'm saying that in the i.i.d regime, if you use just purification, if you instead of preparing copies of rho, you decide to prepare, if you decide to prepare purification of rho, and there's just some subtlety here, purification of rho that have the same period, because you want to use U1 results basically. So if you impose this constraint that I want to prepare purification of rho that have the same period, then in general, the cost will be higher than what you obtain from quantum Fisher information.
All right, so that's why we take the infimum. So in general, of course, creating a purification of a state is higher than the cost of creating a state, the state law. But what we are saying is that there exists a pure state whose cost is equal to the cost for the state law.
Perhaps we discuss this later offline, but I think if you impose the U1 constraint, in general, the cost will be higher. If you want to get a periodic state, it will be larger than Fisher information, but maybe we can discuss it later.
Thank you.
Thank you for the talk.
Thank you very much.
Any other questions? Well, if not, maybe this is it for the first session of Friday. Thanks to all the speakers, and thank you